Hello there. So, here is a solenoid, and wired to the solenoid is an ammeter, which is going to measure current. And then we have this magnet here. If I take the magnet and I hold it above the solenoid, there's field coming out of the magnet's north pole, going through the loops of the solenoid. So I have a field going through an area, that means there's a flux there. And if I move the magnet, that's going to change the flux. And you can notice the ammeter, when I do that, starts moving. So, when you're able to change the magnetic flux through a loop of wire, you're going to induce a current in that wire. And that concept is known as Faraday's Law. All right, Faraday's Law is going to deal with something called induced electromotive force, or induced EMF. The symbol for an EMF is epsilon here, and it's measured in volts because it's a voltage, it's an induced voltage. So let's consider a bar, a conducting bar moving in a magnetic field. So the bar, since it's a conductor, has free electrons. But when we talk about physics, we mostly talk about conventional current, which is based on positive charges. So when we say positive charge moves one way, we just mean electrons move the opposite direction. So if you use the right-hand rule, where you put your thumb in the direction of the motion of the bar, which is to the right, because those free charges in the bar moving to the right with the bar, the field is into the page, so if you put your fingers into the page, then your palm is going to be facing up. So there's an upward force on the positive charges in the bar. Now, of course, that means the negative charges are going down, but because of that, since negative charge is leaving the upward part of the bar, leaves with the positive charge, we say positive charge moves up, even though we know it's the electrons that actually do the moving. Now, once all the electrons come down here, and you have extra electrons down there leaving it a negative charge, a bunch of missing electrons up here leaving it with a positive charge, you have a charge difference. And because there's a charge difference, you have a potential difference. And that potential difference is induced by moving the wire or the bar in the field. So it's called an induced potential difference or an induced electromotive force. And charge is going to move in this wire until the magnetic force pushing the charges up equals the electric force, because if you have this potential difference here, if you have this charge separation, there's going to be a force on free charges in the wire as well. So you have two forces here, the magnetic force pushing them up, and then because you're creating the charge separation, you get an electric force, which is going to try to push positive charges down. And everything's going to equalize once those two forces cancel out when they equal each other. If you consider the force on any given charge moving in the bar, the magnetic force would be QVB because it's a charge moving in a magnetic field. And then because there's that charge separation and there's a potential difference, there's an induced electric field E, and electric force is EQ. Now, for any given charge, the charges cancel out. When you use some algebra, you get this, and then when you solve for epsilon, and epsilon equals BVL, where B is the field strength, V is the speed of the bar moving in the field, and then L is the length of the bar, and that gives you the induced EMF when you have a conducting bar moving in a magnetic field. Now that's a formula that's always going to be true, but that's also a derivation you should know how to do. You just set the magnetic force equal to the electric force. Now here's a very similar setup. We have a bar moving in a magnetic field. However, now the bar, if you see, is on kind of on rails, and it's connected to a circuit. So there's a circuit running around here with a resistor. And we're going to look at what happens after a certain time as this bar moves through this field and through this circuit. So here's the bar after it's moved a little bit. And in that time that it was moving delta t, it covered an area of A. So the bar moved through an area, so we have a magnetic field running through this area. Now hopefully you're kind of clued in to what it means when you have a field and an area together. We're going to have a flux through that area. And the flux is BA, where B is the magnetic field strength and A is the area. Now let's look at what the area is. So we have a rectangle here. The length is L, which is just the length of the bar. And then let's say delta t is the time that the bar has been moving. The distance it moves in the x direction is its velocity, because it's moving at constant velocity, times delta t. So when you substitute that into the formula for the area, you get BV delta TL. And I'm going to divide that by delta t there. So what we have here is phi over t equals BVL. So the flux over time equals BVL. And we just drive what BVL means. BVL, that's the induced EMF. So this says that the rate of change of the flux, or the flux over time, equals the induced EMF. And that's Faraday's law. Faraday's law basically says if you have a magnetic field going through an area bounded by a circuit, so if you have a field going through the area, you have a flux. If you change that flux, you're going to get an induced EMF in that circuit. And mathematically, that means the induced EMF equals the rate of change of the flux. So it's the change in flux over the change in time, or in physics C terms, the derivative of the flux with respect to time. And of course, there's this negative sign here. We'll talk about that in a moment. That's Lenz's law. Here's Faraday's law in action. So I have a north pole of a magnet, south pole of a magnet, magnetic field going that way. And since the field goes through an area between loops of wire, I have a flux. Right now I have no flux because the field's not going through the loop, but if I put it this way, then I have maximum flux. And magnetic flux, that's BA cosine theta. In this case, I can't change the B because these are fixed magnets. I can't change the area of the wire because the wire is also fixed, but I can move the wire like this. I can rotate it, and I can change the cosine theta and cause a change in flux. And if I spin it, I'm going to change the flux, and if you notice when I do that, the lights light up, and that's because there's current in the wires here because there's an induced EMF. If you recall all the way back when we did mechanics and we were going over Newton's laws, which you should, Newton's third law says that for every action, there's an equal but opposite reaction. That was referring to forces. But the same principle applies to electromagnetism. So I have a flux going through a coil of wire. The coil of wire is going to have a current induced in it, and that induced current is going to create a magnetic field, an induced field, to oppose the change in flux. Mathematically, that's the minus sign in Faraday's law. So Faraday's law says that there's an induced EMF in a wire, or a coil of wire, and that's equal to the rate of change of flux. That's Faraday's law. Lenz's law says it's in the opposite direction, so it has the opposite sign, and that's where the negative sign comes from. Hello again. Let's look at Lenz's law in action. So if I move the magnet into the solenoid, the current's going to go in one direction, so the meter moves to the right. When I pull it out, the meter moves to the left. So I put it in, it goes to the right, and when I pull it out, it switches directions. Let's look at why that happens. So this was the setup. I have the north pole facing down going into the solenoid, and that means the magnetic field was facing down because the magnetic field comes out of north. And then since the magnetic field through the loops is going down, that means that the flux is also down through the loops. Now, since the magnetic field, or the magnet, is getting closer, that means the magnetic field is increasing. Likewise, the flux is also increasing. So in general, for any vector quantity, if a vector quantity is in a certain direction and it's increasing, that means that the change in that quantity is in the same direction as that quantity. So if the field is down and increasing, or the flux is down and increasing, that means that the change in flux is down. Lenz's law says when there's an induced current, which there is in this case because there is a change in flux, it's going to be induced to create a field that opposes the change in flux. So the change in flux is down. That means the induced current is going to try to create a field that's up. So we're going to use the right-hand rule. We know that the induced current is going to try to create a field that's upwards. So if you put your thumb upwards for the field, then your finger's going to curl in the direction of current. So in this case, we get a counterclockwise current. Here's where the magnet's brought out of the field, and in this case, the magnetic field is still down because magnetic field goes into south, so we still have a downward-facing flux. But in this case, we're bringing the magnet away from the solenoid. So if we have a downward-facing flux and we're going away from it, that means we have a decreasing flux. So with any vector quantity, if the vector quantity is in a certain direction, but it's decreasing, that means the change in that quantity is in the opposite direction. So we have a change in flux that is upward. So the induced current is going to try to create a field to oppose the change in flux. So the change in flux was up, so the induced current is going to try to act to create a downward-facing field. So if you use the right-hand rule, put your thumb in the direction of the field, your thumb goes downwards, your fingers will curl clockwise. So now the current's going to switch direction and go clockwise. Example A is a similar scenario. So in this case, we have a conducting loop that's placed next to a current-carrying wire as shown. determine the direction in the loop, as in the direction of current in the loop, if the current in the wire is increasing. All right, so by the right-hand rule again, if you put your thumb in the direction of current, now your fingers are going to curl in the direction of the field, so the field in this loop is into the page. When you increase the current, the field into the page is going to increase, and since we're looking at a field going through a loop of wire, that means we have a flux. So when the field increases, the flux also increases. And if the flux is increasing, that means that the change in flux is in the same direction. So the change in flux dV dt is in the same direction, which is into the page. Now the induced current is going to create a field that's going to oppose the change in flux. So the change in flux was into the page. The induced current is going to create a field that is out of the page. So you get the direction of that induced field by using the right-hand rule. So you put your thumb in the direction of the induced field, and your fingers will be the direction of the induced current. So by the right-hand rule, your fingers would curl counterclockwise. Your induced current in this case is going to be counterclockwise. Real quick, part B looks at the opposite case. This is where the current's going to decrease. Now, since it's the opposite, we know the current's going to be clockwise, but let's look at why. So in this case, we have a flux into the page because there's a field into the page, but now the field, and therefore the flux, is going to decrease. Now, if the flux is decreasing, that means that the change in flux is opposite the direction of the flux itself. So if the flux is into the page and decreasing, the change in flux is out of the page. And remember, the current's going to try to create a field opposing the change in flux. So the change in flux is out of the page. The induced current is going to create a field into the page. And by the right-hand rule, if you put your thumb in the direction of the induced field, which is into the page, your fingers will curl clockwise. So in this case, the induced current is going to be clockwise. Example B, a magnetic field has a strength given by this field function here and acts out of the plane of this page. A circular loop with a radius of 2 has the field act right through it. Find the induced EMF in the wire, this loop is a wire, as a function of time. Okay, so this is a place where we're going to use Faraday's law. So the induced EMF is negative d phi dt. And of course, phi for a field acting through a loop is BA cosine theta. That's our flux. Now, cosine theta, we don't have to worry about too much because the area vector of this loop would be in or out of the page, and B is going to be parallel to that, so there is no cosine theta to worry about. And then also, the area is constant. It's a circle with a constant area of pi r squared. So I'm going to kind of pull that out of the derivative, so it's just going to be the area times dB dt. And then the derivative of b, it's a pretty easy function. It's a polynomial, so just use the power rule. So it's 4t minus 2 for the derivative. And there we go. We can plug in numbers. So pi r squared, that's the area, and dB dt is 4t minus 2. And you simplify, you get 16 pi t squared minus 8 pi. Part A was pretty easy. Students typically do well with the math in these types of questions. Where they're going to make mistakes is when applying Lenz's law. So part B is to define the direction of the current in the wire at time t equals 2 seconds. Now the important thing for Lenz's law is the current is going to be induced such that it creates a field to oppose the change in flux. So in order to find the change in flux, we have to find out whether the field itself is increasing or decreasing. So you know the field is out of the page. Does that mean the change is out of the page, or is the change into the page? So let's go ahead and find dB dt. We know it's 4t minus 2. All right, so there's our dB dt function. Now if you find out at time t equals 2, is that positive or negative? Because remember, calc 1, if the derivative is positive, the function's increasing. If the derivative is negative, the function's decreasing. So there's plugging in 2 into that function, and we get dB dt is positive 6. So our derivative is positive. That means that our field function is increasing at this point. So b is increasing because its derivative is positive. So since b itself is out of the page and it's increasing, that means that the change in it, if something is increasing, the change in that thing is in the same direction. So the change in flux is also out of the page. Since the change in the flux is out of the page, the induced EMF is going to try to oppose that. So it's going to try to create a field into the page. So we're going to use the right-hand rule for a magnetic field, an induced field into the page. So this is the right-hand rule where you point your thumb in the direction of the field, so that's into the page, and your fingers are going to curl clockwise. So the induced current is going to be clockwise by the right-hand rule. Example C is a pretty common AP Physics question. It's also somewhat infamous. It's where you mount a loop of wire, a little circuit, on top of a cart, and then you send that cart into a magnetic field, as one does. So example C, the cart shown in the figure has a mass of 2 kilograms and moves towards a uniform magnetic field of magnitude 2 teslas into the page, as shown. Attached to the cart is a rectangular loop of wire that is 0.1 meters by 0.2 meters, and there's a resistance in that wire of 2 ohms. Indicate the direction of the current in the loop when the front end of the loop, so just the front wire there, enters the field. This is just a right-hand rule question. So since the wire is a conductor, this front wire here has free charges in it. And again, it's electrons that are moving, but we'll say there's free positive charges. And because the car's moving to the right, those charges are moving to the right. So using the right-hand rule, you put your thumb in the direction of velocity, which is to the right. Fingers at the field go into the page, and then your palm's going to point upwards, which means those positive charges are going upwards. And since positive charges are going upwards, that means conventional current is going upwards. In reference to the loop as a whole, if current in the front end is pushed up, then we just get a counterclockwise current. Part B, when the front of the cart reaches the field, it has a speed of 5 meters per second. Calculate the force on the cart. So there's 2 forces we have to look at here. The first force was the one that caused current in the wire. So charges here were pushed up that caused a counterclockwise current. And now let's use the right-hand rule for those currents, because those currents are now moving charges. And if I use the right-hand rule here, thumb up, fingers into the page, I get a force to the left, which is a resistive force on the cart. If I use the right-hand rule on the top, thumb to the left, fingers into the page, I get a downward force. There's no force on the left end because there's no field. And on the bottom of the cart, I get a force upwards. So the 2 forces on the top and bottom of the cart, those are going to cancel out. And we have a net force to the left, which is going to be the force on a current carrying wire in a magnetic field, which we know is Bill. Part C, calculate the force on the cart when it is entirely inside the field. So let's consider the moment when it first enters the field. So there was that counterclockwise current. Let's take when it first enters the field and that counterclockwise current is still there, because the current's going to go away. And just like with the top and the bottom wires, the right and the left wires are going to cancel out in terms of the force. So on the right wire, by the right-hand rule, fingers into the page, thumb going up, you have a force to the left. On the back wire, thumb down, fingers into the page, you have a force to the right. So those 2 forces are going to cancel out, and you're going to get no net force. So the force is going to be 0. And that's because, Bill, there's the same length for both of these wires and the same current. Now, eventually, the positive charge here is going to try to move up, and then you're going to get the current to cancel out, so the current will actually drop to 0 as well. But the force for the entire time that the cart's in the field, the force will be 0, so it'll move at constant velocity once the entire cart enters the field. Anytime you see Faraday's law in action, you're really never going to see one single loop of wire. You're going to see a bunch of loops of wire, like in a solenoid, which is this down here, or a toroid, which is the donut solenoid. That's what Faraday used. And the reason why is you get an induced EMF, you get a change in flux every single time that you have the field going through an area. So you have a bunch of areas if you have a bunch of loops. So for each coil of wire, for each loop you have an area for each loop, so you get that induced EMF each and every time. So this is kind of the full version of Faraday's law here, where n, that's your number of loops. As you can see, it's directly proportional to the induced EMF. So as n goes up by n number of times, the EMF will increase by the same exact factor. So treating the front end of the cart as a wire magnetic field, the force on it is Bil, B-I-L. B is given, L is the length of the wire, which is how long the front of the cart is, which is given as 0.1 meters. And then the current, that's the induced current. And the induced current is going to be the induced EMF over R. So the equation becomes B induced EMF over R times L. And then this is the induced EMF in a bar moving in a magnetic field, which is already derived. It is BLV, because it's moving at a speed V. And then putting it all together, you get b squared L squared V over R. And now you can just plug in numbers. So it's 2 Teslas squared times 0.1 meters squared. The speed is given as 5. And the resistance was given as 2. And plugging in numbers there, you get 0.1 newtons as the magnetic force. Example D, a metal wire coil of radius 0.5 meters has 1,000 loops, which forms a solenoid. The solenoid is placed in a 500 millitesla magnetic field. So you have a magnetic field going through it like that. The field suddenly drops to 0 teslas in 10 milliseconds. What is the induced EMF? So Faraday's law, the induced EMF is negative n, because there's a bunch of loops here, d phi dt. And they're in the same direction. The area vector and b are in the same direction, so we'll ignore cosine theta here. So you have negative n. Phi is BA. And then A is constant, so I'm going to pull that out of the derivative. So it's just dB dt. And now I'll plug in numbers. So 1,000. The area, it's a circle, so it's pi r squared. And it drops to a final field of 0 from an initial field of 500 milliteslas. So that's 10 to the negative 3. And that happens in a span of 10 milliseconds. When you plug in numbers, you're going to get 25 pi over 2 volts. Example E is a calculus-based question. So we have a square loop, side length of 0.25, and it encircles a solenoid with 1,000 loops, a diameter of 0.1, so a radius little r of 0.05. And the solenoid has a length L of 0.2 meters. And the square loop's plane is perpendicular to the axis of the solenoid. That just means that there's no cosine theta to worry about. The flux goes straight through, no angle involved. The current in the solenoid is given by that function there, 100 times 1 minus e to the negative t over 5. Calculate the induced EMF in the loop as a function of time. So this is a Faraday's law question. Induced EMF is negative d phi dt. And phi here is going to be BA. No cosine theta because, again, the flux goes straight through. B, this is B for a solenoid, which we used Ampere's law to derive this. It was mu sub 0 Ni over L. And in this case, the current is variable, so it is I of t. And then for the area, this is the area that actually has flux going through it. So if you look at the picture here, the square loop is bigger than the solenoid. There's only flux through the solenoid because there's only field through the solenoid. So there's no flux here or here because there's no field there. If the square loop were smaller than the solenoid, we would use the area of the square. But since it's bigger, we only use the part with field going through it, which is the solenoid's area. So that's going to be pi r squared, where little r is the radius of the cross-sectional area of the solenoid. All right, so we have epsilon equals negative d phi dt. So phi is BA, so B is mu sub 0, and I of t, I'll leave it as I of t for now, over L times pi r squared dt. And before I do the derivative there, I'm just going to pull out all the constants. So I have mu sub 0 n pi r squared over L, and that's going to be times d current d time, so that's going to be 100. 1 minus e to the negative t over 5 dt. And then for the derivative, it's a pretty simple derivative, so we have all the constants out front again. And then that derivative is just going to be 20 e to the negative t over 5. And I'm not going to plug in numbers here because I'm kind of out of room, but when you do, you're going to get that epsilon of t equals negative 0.001 e to the negative t over 5. And that's your answer. Example F is a classic physics C question where you have a bar falling in a magnetic field. So this question, you have a conducting bar of mass m and length L connected to 2 long conducting rails. The 2 rails are connected by a resistor of resistance R at the top. and between the rails, the whole apparatus is in a magnetic field of magnitude B, which is directed into the page, and the bar is released from rest and slides without friction down the rails. Part A says solve for the terminal velocity. Before we do that, let's look at what's going on here. So you have to use the right-hand rule twice. So the first time we're going to use the right-hand rule, we have this bar. It's a metal conducting bar, so there's a bunch of free charges in that bar. And those free charges are moving down because the bar itself is moving down. And if we use the right-hand rule, point the thumb down, fingers into the page, you're going to have a magnetic force pushing the free charges, the positive charges in that bar, so electrons in the opposite direction. You have positive charges going to the right in the bar. So that's the direction of conventional current in the bar. Now, we had charge moving down because the bar is moving down, but now we also have charge moving right. So you have to apply the right-hand rule again, because now you can put your thumb to the right, because there's charge moving to the right now, finger still into the page. Now you're going to get a magnetic force upwards, and that's going to be a resisting force as it goes downwards. So to solve for the terminal velocity, we have a force question. So we're going to draw a picture, label the forces, and do F equals ma in the direction of motion. So here's the free body diagram. You have your bar, gravity, that's your positive force because it's in the direction of motion, goes down, and then the magnetic force goes up. So the sum of the forces in the y direction equals ma, and that's going to be mg, the positive force, minus the resistive force Fb. And this question says solve for terminal velocity. We know at terminal velocity, it no longer accelerates, so the acceleration is going to be 0 at terminal velocity. So we can say a 0, which means that mg equals the magnetic force, which this is a bar with a magnetic force on it, so that force is going to be Bill. And then the induced current on that bar, that's going to be the induced EMF over the resistance in the wire, which is R. And now this is a bar moving in a magnetic field. At the beginning we derived the induced EMF if you have a bar moving in a field, and that's going to be BLV. So mg equals magnetic field, induced EMF, which is BLV, over R, so that's your induced current, times L. And then simplifying it a little bit, you get mg equals B squared, L squared, V over R. And then solve for V, and that V is your terminal velocity. And that's going to be mgr all over B squared, L squared. So that's the expression for terminal velocity. We're going to hold on to that for when we get to part B, because we're going to use it. Part B says to derive an expression for the velocity of the bar as a function of time until terminal velocity. So at terminal velocity, we had the two forces, magnetism and gravity, equal each other. That's not true until terminal velocity. So until then, the magnetic field is going to start off at 0 and grow as a function of velocity. So we have F equals ma, and if you have calculus, you have A is dB dt. And that's going to equal mg. And then our expression for magnetism from up here was B squared L squared V over R. So this is a case where we have dB dt as a function of V. That makes this a differential equation, so we're going to have to separate the variables and then integrate both sides. So whenever you're separating the variables for, this is a drag equation. This is going back to mechanics. It's the same exact situation, except for instead of having BV as your resistive force, now you have B squared L squared over R times V as your resistive force. So the easiest way to separate the variables is to get positive V by itself. And to do that, we can multiply both sides of this equation by negative R over B squared L squared. I'll leave us with, on the left side, we're going to have negative MR over B squared L squared times dV dt equals positive V, that's multiplying this by that, minus mgr over B squared L squared. So I'm going to make a substitution here. This whole thing, mgr over B squared L squared, that's our answer to part A. That's actually the terminal velocity. So I'm going to rewrite this equation.
with VT for terminal velocity subbed in for that, and that just is going to save some writing because this is going to be a lot of steps. And with that, I can separate the variables, so I can divide all this over here, and I get dv over v minus terminal velocity equals negative b squared L squared over mr times dt. And now I integrate both sides. And to that, I have to choose the bounds. So as always in physics C, the integrals for time are always going to be 0 to our variable time t. And the integrals for velocity are going to be, well, this is going to be a bar that's dropped from rest. This question says that the bar is released from rest. So it's going to start off at 0 for its velocity, and then it's going to go to some velocity v at t. Okay, now we can just integrate both sides. The left side, we've done this before, so I'm not going to go through all the details, but this is going to be ln of v evaluated from v of t to 0, or 0 to v of t. And on the other side, we're going to get negative b squared L squared over mr times t. Now you plug in the bounds on the left side. You get ln v of t minus v sub t minus ln negative v sub t equals negative b squared L squared over mrt. Now I can use properties of logs to say that the left side is ln v of t minus v sub t all over negative v of t equals this mess over here, b squared L squared over mr times t. All right, now I can do e to both sides and get v of t minus vt all over negative vt equals e to the negative b squared L squared over mr times t. And when I simplify, I get my final answer as being the velocity as a function of time equals the terminal velocity times 1 minus e to the negative b squared L squared over mrt. And that's the function. So here's our graph for velocity. It's going to start at 0 and go to the terminal velocity, of course, asymptotically like that. So here's the entire process all in one place for the bar falling in a magnetic field. You can see we have the downward force of gravity, the upward magnetic force, which is Bill. The current is the induced EMF over R. It's a bar moving in a field, so the induced EMF is BLV. Then you go through and have your integral, separate the variables, plug in the bounds, and then solve using the process that we use in mechanics. And there you go.
So that's Faraday's law. It's not that difficult of a topic, but it is very, very, very important. And basically what it says, if you have a coil of wire and you send a magnetic field through it, then you have a flux. If you find a way to change the flux, you're going to get an induced EMF. And flux is BA cosine theta, so there are 3 ways to change flux. They're pretty obvious: change the field, change the area, or change the angle. And in the real world, in a power plant, they spin a turbine, so mostly they're changing the angle to create an induced EMF. And then Lenz's law basically says if I have a change in flux one direction, so if I move this in here and increase the flux that way, the induced EMF is going to try to create a field that way in the opposite direction. And then flux linkage basically says, yes, you have an induced EMF, but you want to have a lot of induced EMFs, so you have a lot of loops. And that's the full version of Faraday's law, negative n d phi dt. And then really common physics C type question is about a bar moving a magnetic field. Very, very common question. So when a bar moves in a field, you're going to have an induced current in the bar. And that induced current is always going to cause a magnetic force. That's going to be a resistive force on the bar. And that resistive force can be velocity dependent. And yeah, that's Faraday's law.